Let's remember where we left off last time. We said that if you defined a function in this new strange way, that is where x is the upper limit, which would translate into the right endpoint of the interval of integration. So integral constant a to variable x of some f of t with respect to t. This is the thing that we talked about a bunch yesterday that we called the accumulation function. And the first fundamental theorem of calculus, which is the last thing we did yesterday, said that if you take the derivative of this accumulation function with respect to that x variable, which is that upper limit, well, it's about the simplest formula we've probably seen in calculus. It is simply this function, the integrand function, evaluated at that x. And I think at the end of class we looked at a few examples of how you would take derivatives if, for example, this x was a more general function of x. I think we also looked at what would happen if the variable was in the lower limit and the constant was in the upper limit. So we looked at a few of those examples of how you would actually take derivatives of different types of accumulation functions. And we proved the first fundamental theorem. Now, think about what it's saying in the picture. So again, with our usual visualization here, if I had, let's say this is f of t, so this is t, let's say that's a, so of course if I stop right here at t equals x, I know that f of x is the integral from a to x f of t dt, which I would naturally interpret as the area under that curve in between a and x. So far so good? And what we're saying is when you take the derivative of that function, what you get is little f of x. Okay, now, where is little f of x in this picture? Isn't it just this value? It's just whatever that y value is. Everybody agree with that? So far so good? Okay, so let's say I make a little rectangle here. And let's say, just for convenience here, let's say the width of this is 1. Okay, so that means what's the area of this green rectangle? It's 1 times the height, which is f of x. Agreed? Yes. Now, not f of 1, but f of whatever this x value is. So when I say 1 here, I mean the width of this little rectangle is 1. So what we're saying is, if this is x, what's this value right here? X plus 1. And that means the width of this rectangle is 1 and the height is f of x. F of x because I'm using this function value right here. Alright, now, roughly, is this true? If I increase this x to x plus 1, then of course what's the new area under the curve? It would be everything from a to x plus 1, which would include all of that stuff, right? Now when I ask you what is big F prime, remember what big F is telling you. It's supposed to be the area under f of t from t equals a to t equals x. What is f prime of x? It should be the rate of change of the accumulated area with respect to x. And what's x? X is the stopping point, that right endpoint of that interval. So what is big F prime? It's how quickly the area is being added as you increase the x. So do you agree that roughly, and this is roughly as in an approximation, when I increase x from this value to this value, isn't the green rectangle approximately how much area I'll be adding? Because how much I'm really adding when I increase from x to x plus 1 is all of this, and the green area is everything inside this rectangle. Well, I say approximately I'm adding that area of that green rectangle because the only part I'm missing is this little red part up here. And do you agree that the smaller this number is, then the closer that green rectangle will be to a good approximation of how much area is being added instantaneously if I start at x and then increase that right endpoint a little bit. In that sense, big F prime, which is supposed to be the rate of addition of area as x increases, well, roughly it's the area of that green rectangle. And so, of course, what we're saying is f prime of x is going to be the approximation of how much area is added when I increase x a little bit. And of course, I know that approximation gets better and better and better the closer I get to x. So picture-wise, this is where we get the idea that the derivative of the accumulation function is just the value of the function itself that we're graphing at this x value. Now that's the meaning in the picture, but what we really need the first fundamental theorem for is get to the second one. And so when you read in books about the seminal moments in calculus and the big theorems, when they say fundamental theorem of calculus, you can't have one without the other. Well, actually, you can have the second part without the first part, but the second part is the one people actually have in mind when they say fundamental theorem of calculus, which says if f of x is continuous on the closed interval a to b, so this sounds just like the first fundamental theorem of calculus, then when I calculate the definite integral a to b f of x dx, and remember right now what this means. The only meaning we have for that so far is that it's the limit as n goes to infinity of a Riemann sum. Theoretically, that's the only method we have so far to calculate a definite integral, which is normally thought of as area under a curve. But the fundamental theorem of calculus says that we can calculate that definite integral by subtracting f of b minus f of a. That is where f prime of x equals f of x, i.e. big F of x is any antiderivative of little f of x. So this is the theorem that's giving us a connection between the limit of a Riemann sum, which is what this is, and some sort of expression that involves antiderivatives. And if you think back to the example I talked about a week ago, where we were looking at that velocity graph, and we figured out that the area under the velocity graph was actually the displacement between two times. And of course, how do you figure out displacement? You take the difference of positions at 2 times. Okay, so that made us think that finding area under a curve had something to do with taking antiderivatives. Because if we're saying the area under a velocity curve is actually just the difference of 2 positions, where position is the antiderivative of velocity, it seems like there's a big connection there. And this is the theorem that says what that connection is. It says that area under a curve, which is the definite integral, is actually equal to the difference of 2 antiderivative values. Okay, where are you calculating those antiderivatives? Simply at the 2 endpoints of the interval. So for example, before I prove this, let's just do a real simple example. Actually, let's do your sine one that you were talking about. So the question was, what's the integral from 0 to pi over 2 sine x dx, which of course we're saying should be this area right here. So if this is 0 and this is pi over 2, this integral should represent this area between 0 and pi over 2 under the curve above the x-axis. Okay, so notice this does look like an a to b f of x dx, and my fundamental theorem up there says all I need to do is find an antiderivative of little f, evaluate at b, and then subtract what I get when I plug a into that same antiderivative. Well, in this case, if little f is sine x, what's an easy antiderivative of sine x? Okay, so Ruben's given me the answer already. We're going to change one thing though. You're right except for one thing. Is the antiderivative of sine cosine or negative cosine? Yes. Okay, I'm going to have to say negative cosine, right? Because I know the derivative of negative cosine is sine. And so what this theorem is saying is what? Take this antiderivative, that's the f that we're talking about. I plug in the upper limit, which is pi over 2, and then I subtract what I get when I plug the lower limit into that antiderivative. So just to be clear here, when we're talking about this expression in the theorem, we're saying the big F is the minus cosine, the b is the upper limit in the integral, that's the pi over 2, then you are subtracting that same antiderivative with the lower limit plugged in. Now what does this turn out to? Cosine of pi over 2 is 0 minus, what's negative cosine of 0? What's cosine of 0 to start with? Yeah, that's 1. And of course that works out great because that means the inside here is minus 1, which means the answer here is 1. Okay, which means the area under the sine curve, and actually if you hadn't ever seen this fact before, this is another one of those very, in my opinion, spooky things, that it turns out if you take just one of these loops of the sine curve, let's say that loop right there, what is that area right there? Yes, does everybody see that? The area of that loop, inside that loop, is 2, because we just calculated half the area. It is symmetric around pi over 2. So I think it's pretty weird that the area under a trig function ends up being an integer value. Yes, it's very crazy. Another question, as long as we're talking about this one. So we're saying what? This is pi, and we're saying this is negative pi. What's the integral from negative pi to pi of the sine function? Everybody agree? I think what we just came up with is this area is 2, and I would get that by integrating from 0 to pi. What am I going to get if I calculate the integral of this part, that is, integral from negative pi to 0 sine x? Yep. Anytime that curve's all below the x-axis, I know the integral is going to be negative, and it's going to be the negative of whatever that area is inside that loop. Well, they're both the same and they cancel out. And that makes sense because the sine function is an odd function. And this is going to be true for any odd function. If you integrate from negative a to a for an odd function like the sine function, you're going to get 0. So this would be true for x cubed also. If I integrated from, say, negative 3 to 3 x cubed, I know that would be 0 because I know what the x cubed function does. The area inside that part and the area inside that part would be the same. One of them would be positive, the other one would be negative, and they'd cancel out exactly. Alright, now, back to our fundamental theorem real quickly, which says if I want to evaluate this integral, this definite integral, I just find an antiderivative, I plug in b, plug in a, and subtract the 2. Okay, the proof is very simple. It's again kind of weird that such a monumental proof ends up, or such a monumental theorem has such an easy proof, but of course it's built on so many other things we've built to this point. Okay, so we know that, let's call it g of x equals a to x f of t dt is an antiderivative of f of x. Does everybody agree with that? If that's what g of x is, if that's how I'm defining g of x, then what is g prime of x? And this would be by the first fundamental theorem. Yes, that's right. In fact, I'll just put it this way. We're saying that you're taking the derivative with respect to x of this integral a to x, where that x is the upper limit of f of t dt. And that was the whole point of the first fundamental theorem, that when you do that, what you're going to get is the integrand, the little f, evaluated at that x. Okay, so that's a fancy way of saying that this g that we're talking about is an antiderivative of f, because the derivative of g is f. Let me just write that down explicitly. So g of x is an antiderivative of f of x simply because g prime is f. And of course this is where we needed part 1 of this theorem, is to get this idea of the derivative of that integral being little f of x. So now, suppose big F of x is, let's say, any antiderivative of little f. So suppose big F is just any other antiderivative of f you want. So far, so good? Okay, what do you know? What do you know about all of the, let's say, antiderivatives of f. What do they all differ by at most? Yes, only by a constant, right? So if we're saying big F is an antiderivative, and we're saying big G is also an antiderivative, well, that means one of them is just the other one plus a constant at most. So far, so good? Okay, so that means if I wrote out what f of b minus f of a is, well, if f of x is equal to this, that means f of b would be g of b plus c, and it means f of a would be g of a plus c. Okay, right away, what's going to happen to those c's? Okay, which means it's going to end up here in the answer. If you notice, our formula up here says when I evaluate this definite integral, I'm just using antiderivatives, and there is no mention of any constants of integration. Okay, that's because those c's are going away. What's left is g of b minus g of a. Good, yep. Now let's write out what is g of b. Okay, go back to what g of x is. Here's g of x. What's g of b? It would be the integral. Not quite. Go right from here. If this is what g of x is, okay, Ethan says it's the integral from a to b, right? Because when you take g of a number, where does that number go? It goes right there. So if I say what's g of b, it should be integral from a to b f of t dt. What's g of a? It would be integral a to a. What's the integral from a to a? Yep. Okay, so that means that's all gone. That's all zero. So what's left is just integral from a to b f of t dt. He is fast. I'm laughing on the inside, trust me. So, notice where we started. We're saying that the definite integral is equal to what? It's equal to this, where f is any antiderivative of the function. So when I say any, I mean if I put a constant in there, it's not really going to make any difference because you would subtract that constant from itself. So the custom is when I take the antiderivative to use this theorem, I just make the constant 0. So when we did that problem a minute ago and took the antiderivative of sine, we didn't say the antiderivative was minus cosine plus 2. We just said it was minus cosine, as in minus cosine plus 0. So from here on out, if I want to do something like integral from 1 to 2 x squared, which obviously we've done this the hard way, right? In fact, let me review real quickly for you. This area should be what? It should be limit as n goes to infinity of summation k equals 1 to n, 1 plus k over n squared times 1 over n. That's the correct Riemann sum formula, because delta x is 1 over n, and if I was using right endpoints, the ck's would be 1 plus k times delta x, which would be 1 plus k over n. And so let's do this real quickly for a review. It would be k equals 1 to n. I would expand out that square, and I would get 1 plus 2k over n plus k squared over n squared, all all of that times 1 over n. That would be limit n goes to infinity. This might be the time I want to split everything up into 3 sums. The first one would be 1 over n sum k equals 1 to n 1 plus 2 over n squared sum k equals 1 to n of k plus 1 over n cubed sum k equals 1 to n of k squared. And then I would just substitute for each one of these sums an equivalent expression using one of my little summation formulas. Although this first one, well, what's the sum k equals 1 to n of 1? What happens when you sum up 1 n times? So if you had 1 plus 1 plus 1 plus 1 n times, you're just going to get n. So that means this first one is just 1 over n times n, which is 1. This next one is 2 over n squared times n plus 1 over 2. The last one's 1 over n cubed times n plus 1 times 2n plus 1 over 6. And so if I calculate that, well, the limit of the first part is 1. This part looks like a 2n squared in the top and a 2n squared in the bottom for the leading terms, which means the limit of that part should also be 1. And then this last part down here, the leading term in the top is 2n cubed. The bottom is 6n cubed. Should be 1/3. Yep. So put that all together and you have 2 and 1/3. You have 7/3. Alright, now, what does our fundamental theorem say? It says if I want to calculate 1 to 2 x squared dx, I take the antiderivative, so let me write this up here. I take the basic antiderivative of x squared. Okay, what's the basic antiderivative of x squared? Power rule says x cubed over 3. Good. Now, normally I would have a plus c there, right? But in this case, I'll just ditch the c. And here's how I'm going to write this. This is standard notation. I'm going to say the answer to this is the antiderivative of x squared evaluated from 1 to 2. So this little vertical bar notation just says I'm going to evaluate this function first at this number, then at this number, and I'm going to subtract the two results. Meaning, first I'm going to plug in 2, then I'm going to plug in 1. And of course when I do the first one I get 8/3, and when I do the next one I get 1/3, and my answer is 7/3. Now, does this mean you don't have to do Riemann sums anymore to find areas? Yes, except I will ask you to do a Riemann sum in the homework a little bit, of course, and on the test you're going to have to do Riemann sum at least once, maybe twice. But all other times you've got a new way to find values of definite integrals now. No, you will not have trig Riemann sums on the test. That's just for you to look at in the homework. The only thing normally expected of Calc 1 students is that they be able to do areas under polynomial curves using limits of Riemann sums, which is the only thing we've really focused on in class. Let's try a few more, see if we have the idea. Here, let's try a real generic one. Let's say -2 to 2 x cubed minus 2x plus 3. Okay, so first thing, find the antiderivative. Antiderivative of x cubed, yeah, it's a race. Somebody else should get in this too. You have microphones too. That's what microphones are for.
It's going to be 1/4 of 2 to the third minus 1x 1x squared plus 3x, and the x it'll be evaluated from -2 to 2.
Yep. Now let's stop there and make sure everybody's okay so far. Look good? This next part is just, crunching numbers, but obviously this is where you could make a sign mistake or something. Use your calculator if you have to. The mistake that some people will make...
It's a constant.
Say again, Ruben?
Well, it's a number. Well, she asked like y 3x, and since 3 is by itself, you're adding like an x when you take the antiderivative, so you just add it to x.
Yes. Yep. Just remember, anytime I take the antiderivative of a constant, it's always cx. Because what's the derivative of cx? It's just c. So the real question is, what is the antiderivative of 1? And the answer is x. And in this case, what Ethan's saying there is I'm going to have to evaluate. So I'm going to plug in 2. Let me just write down what that is. So 2 squared, 2 to the 4th, sorry. 2 to the 4th over 4 minus 2 squared plus 3 times 2. And Ruben's saying 1.
So, yeah, that's 1 minus 4, so -3 plus 6, so +3.
Almost. Check your first one again. Your 2 to the 4th divided by 4.
Oh, 2 to the 4th, okay, never mind, I was thinking 2 squared.
Yeah. Okay, where's the one place that people make a mistake early on when they first learn this? You have to remember that now you're going to subtract everything that you get in this function when you evaluate it at -2. So, depending on how you want to write that down, what you'll see a lot of people writing is a big subtraction and then a bracket where they put all of that stuff inside the bracket, namely -2 to the 4th over 4 minus -2 squared plus 3 times -2. And that probably would be the safest way to do it. That way you're not going to make any sign mistakes. And of course I know this part is again a 4. I know this part is again a -4. Oops. I don't like that. But notice this time, what's this one? It's actually -6. But of course, when I end up doing this subtraction out here, I'm going to get a +6 again anyway. Yeah, so total is 12, right? Those are gone, those are gone. What's left is a 6, and then plus a 6. So we're saying it's 12. Are we still able to do Riemann sums for things like this? Yes. I'm not saying you have to go back and do that for every one of these, but once in a while for practice, this would be a good place to practice your Riemann sums. Or, conversely, if you're doing a Riemann sum problem, now you have a way to check the answer. It's very quick. Okay, any questions so far about how the rule's working? I would say this is akin to, yeah, it is fun, especially after you've sort of been wading through all this stuff with Riemann sums. I'd say this is, akin to all that work we did with derivatives, with limit definitions, and then you come out on the other side and there's a couple simple rules that say the derivative is bang, it's pull the power down, subtract 1. We're at the same point now with integrals. we've just come to the point where evaluating one of these is a really simple thing. Now, one thing, what's the key to being able to do one of these easily? It's that the function has an easy antiderivative. So we're still going to be up against that problem eventually if the functions become more difficult to find antiderivatives for. Well, then this is not so easy anymore. But that's not going to happen in this class. That's more for the next class. When you look in the homework for 4-7, you're not going to have problems integrating any of these things. Now here's a trig one I see. I'm looking at your homework problems. So this is number 18. So let's throw in a trig function mixed with a rational function. Okay, but I still do the same thing. I take antiderivatives, and notice, just to rewrite that last part, this is 4 secant squared t plus pi t to the minus 2. So what's the first thing I do? I take the antiderivative. What's the antiderivative of this guy? Secant squared is one of the nice ones. Yep. Antiderivative of this guy is a power rule situation. Yeah, definitely negative pi t to the minus 1, because we know the rule is to add 1 to the power and then divide by that same new power. And of course negative 2 plus 1 is going to make a negative 1. So that makes negative pi t to the minus 1. Now, what am I going to do with that? I'm going to evaluate it from negative pi over 3 to negative pi over 4. By the way, just a notational thing, it's usually customary when you have 2 or more terms in your antiderivative. When we did this the last time, if I just had one term, it's custom to put a bar. If there's 2 or more terms, it's custom to put it inside a big pair of brackets, and then put your limits out here to say what you're going to do next, which is plug in negative pi over 4. Minus what you get when you plug negative pi over 3 in. And I realize I left a minus off right there. Does that look good so far? I'll just tell you in advance, once you get the hang of this, the only thing you might get caught in once in a while is making a sign mistake. When you're doing this subtraction, it's easy to mess up something with the signs on this second part. So let's see, tangent of negative pi over 4. Real close. Agreed. Negative 1. Which means this part will be negative 4. Beat that. What's this next part here?
I'm sorry for what I started there, but I still won for the record.
Yes, that's right. You won.
Okay, whatever.
Uh-oh.
Man, your class is competitive for no reason. You can't let me win.
I get +4 for that next part. Yep, that's what James says. What's, this guy? And that's not one you maybe know off the top of your head. You might have to look at your little trig wheel for that. It's definitely sine of 60 over cosine of 60. Of course it's negative, so it's in quadrant 4. Tangent should be negative in quadrant 4. Sine of 60 is sine of pi over 3, which is square 3 over 2. Cosine of 60 is cosine of pi over 3, which is 1/2. I'd like to see you count square root of 3 on your fingers. Negative 4 times. Yeah, I think that's right. Agreed. I agree with that square root of 3 one. And then what's this last guy? He's positive. He is 3, but it'll be positive. Now you will end up being negative once I do the big subtraction out here. Inside he's +3. So altogether, it looks like I've got 4 square root of 3 plus 3. So of course I'm not always going to get pretty answers with these. But there's, same idea just with trig functions. Why not negative 3? On the inside, you mean? There was a negative here, and then I plugged in a negative here. And so those two negatives made him a plus. Oh, I see what you mean. No, you're right. I am corrected. This is a plus, but that means this is a minus. Gotcha. Thank you. Everybody catch that? That's right. That should be minus. No, you're right. I just can't distribute or something. Okay, now let's do one more. And actually tomorrow we'll talk about a slightly improved way of doing what I'm going to do in this next problem. But the way I'm going to show you here is the way actually most people really do this in practice. So let's say I want to integrate 1 to 2, 3x plus 1 dx. Okay, what's the difference between this and the previous two problems? You've got a chain rule here, don't you? Which means you're going to have to do a substitution, because you have a u equals 3x plus 1 sitting inside that square root. Alright, so I'm going to show you two ways to do this, and actually this is falling out pretty well, because we'll look at the one way to do it today, and that'll separate it from the other way of doing this that we'll look at tomorrow. You should be able to understand and do both ways. How you actually do one of these problems, let's say on a test, doesn't matter to me. The way you're probably going to prefer to do is the one we're going to do right now. But you definitely need to learn the other way. When we get to Calc 3, you won't be able to do it the way I'm going to do this one right here. You have to learn that other method. Alright, so what I'm going to do is just forget about the limits, ignore those for a minute, and just do the regular antiderivative. And so do this the way you were doing things earlier in the chapter. Make your u substitution. Yep.
You use 3 and then 1/3 outside.
Good. Way ahead of me.
Sorry.
No, you're good.
And then I changed the square root into a 1/2.
Okay. Everybody agree with that?
Then we would add 1, so 2, do the 3 over 2.
And then I would multiply by...
2/3.
Yep. Okay, now normally I'd put a plus c here, right? But I know that when I evaluate with the theorem, I'm not going to have the plus c. So I'm just going to leave it like that, which will be 2/9. Now, plug the x stuff back in, which means 3x plus 1 to the 3/2. There's my antiderivative, right? So that means 1 to 2 integral square root of 3x plus 1 dx equals what? The antiderivative, which is this, evaluated from 1 to 2. Nothing fancy here. We're just saying go off and do the antiderivative and do that separately. And if you notice, the thing I'm emphasizing here is when you did all of this part, I don't include the limits. Now we'll talk about this tomorrow, but you should be able to see that if I start changing the variables, isn't that going to change these limits to something else? Does that make sense? In this original integral, you're saying that x goes from 1 to 2. If you change this variable to something else, that's not an x anymore. That's saying that u is going from something to something. So what I mean is, if you continue to do this problem, and you change everything to a different variable like I'm doing right there, you can't use the same limits that you started out with the 1 and the 2. Meaning, if you wrote a 1 and a 2 here, after you've changed these variables to use, that's incorrect. So what I'm saying is, forget about the limits, just do the antiderivative. Now plug the limits back into the antiderivative now that you've put everything back in terms of x. And of course, what's this? 2/9 is a common factor. I'll just pull that out. And I'm going to plug in 2, which will make 7 to the 3/2. And then I'm going to plug in 1, which would be 4 to the 3/2. Agreed? And sometimes you're not going to get pretty numbers. This one here, I would just leave that one like that. Actually, I'm okay with you leaving the whole thing the way it is. Now this one here would be okay. That's 8. 4 to the 3/2 is just 8. So if you wanted to say 2/9 times 7 to the 3/2 minus 8, you don't have to, but that part can be cleaned up. 7 to the 3/2 is not a nice number, though. It's the square root of 7 cubed, which is a totally irrational number. But of course, if I do need a decimal approximation, I can always get that from the calculator. What do you think? It's not bad at all. You need a lot of practice on this.
I hate the part where we change the integrals, like the numbers.
Yes.
From the A to B.
Yeah. So that's what I'm saying here. Get used to doing it this way first. So if you caught what I was saying right here, I was saying the other way we're going to look at this tomorrow is to do our substitution and change these original x numbers to corresponding u values. And we're going to learn how to do that. But if you're comfortable with the way we did this one, I'm fine with you doing your definite integrals this way when you do a U substitution in this class. It's fine. In fact, after tomorrow you can sort of pick the way that makes the most sense to you. But I'm pretty sure most of you will pick this way. Okay, let's have you look at, let's say 1 through 59 odd. That's definitely a general practice suggestion there. I'm sure most of you are not going to do all those, but you should do as many as you need to get comfortable with it. And then I threw on a few here at the end: 63, 67, 74, 75, 77, 79. Now these ones at the end, yeah, this is 47. These ones at the end here, so these are the general practice for finding values of the definite integral. These are something else, and you definitely need to look at those. You need to do all of those. And I'll talk about those tomorrow before we get into 4.8. So we'll start there. So you're definitely set up to grind on this 1 through 59 stuff. And I think that should come pretty quickly to you.